Assalamu alaikum warahmatullah. Hello guys. Let's talk about practical methodologies in machine learning. Let's get started. So let me to share my screen. Here it is. Practical methodologies chapter 11 in the book of deep learning by Ian Goodfellow and etc. and et al. So during the day-to-day development of machine learning systems, practitioners need to decide a lot of things. Particularly, the practitioners should decide whether they should gather more data, or they should increase or decrease the model capacity, or they should add or remove the regularization terms, or whether they should improve approximate inference in the model, or improve the optimization algorithm, or debug the software of the implementation of machine learning model, and etc. There are different ways to go. And all these operations are at the very least time consuming to try out. So it is important to be able to determine the right course of action rather than blindly guessing. So there should be a right course, right way of trying these methods and having good results, because they are very time consuming and they take a lot of time. So the Andrew Ng wrote the paper. Here's the link, machine learning advice. So these slides are mostly inspired from that and the book of deep learning. So first of all, the first thing to do is that we need to decide which error metric to use and what is our goal. So for example, if it is classification, then the metric may be accuracy, or if it is regression, maybe mean square error, etc. So you should select the metric first, and then what is your goal. So in metrics, one thing is that sometimes in some applications it is impossible to have this error to be zero. It's impossible to reach absolute zero error. And when your goal is to build the best possible real-world product or service, you can collect more data. If your goal is to answer scientific questions, then probably you cannot collect more data, because you will compare the model to the benchmark, to the fixed benchmark. So that's important things, first things to do, to understand what are the performance metrics will fit best for your task. Second thing is that the default baseline model. It is very important after deciding this goal and the performance metrics to build end-to-end system as soon as possible. So when building this end-to-end system, it's very good to use current approaches in the academia, or to build very simple model, maybe starting from feed-forward networks, or if it is images, then SNN, if it is sequence data, then RNN, etc. And basically use the default, the minimum models or algorithms, like maybe for optimization use ADAM or SGD, and it is very good usually to apply early stopping. It doesn't hurt, and it is also good to use dropout. And bench normalization and other kind of regularizations, it is advised to add them later. So build this model, very basic model, and test it and get the results on the trained data and on test data. So after that, you will decide what to do next. So for example, if you check your performance based on your performance metrics, the training set acceptance, if it is acceptable, then we can go forward. If it is not acceptable, then it means that something is poor. It means that your model is doing poor in the training dataset. It may mean that learning algorithm is not using training data that is already available, and it means there is no need to gather more data. There is a problem with the learning model which is not doing good with training set, or maybe your training set is collected poorly or contains very poor, maybe it concludes very poor or incorrect inputs which are required for the target data. And this suggests that you should check your data again in order to collect more clean data, or to go and try more complex learning algorithms, models. If the training set acceptable, the performance in training set is acceptable, then it means go and check the performance in the test set. If the performance in test set is also acceptable, then it means that we reached our goal, which means that our model is working good on the test dataset, and their performance is acceptable, then we are done. If not, if in test set we don't have enough performance metrics, then maybe it is good indication of that you need to collect more data to make it more generalized, or try some regularizations, maybe like batch normalization or another dropout, maybe etc., or L1, L2 regularizations. Or maybe you can also go and try to use hyperparameter tuning, such as weight decay coefficients or other regularization strategies, and try them, and again go to this loop. Is training set acceptable or not? If acceptable, then go and check the test. If the test is acceptable, then you are done. Or not, then try another, and do this loop of repeating this kind of try and out things, which will give you the result of your performance metric you want. So after doing such thing, another good thing of in practice is to select hyperparameters. So there are two ways of selecting hyperparameters. First, manual selection and automatic selection. As you know, manual selection is very time consuming, but the goal of manual hyperparameter tuning search is usually to find the lowest generalization error subject to some runtime and memory budget. So many deep learning algorithms come with several hyperparameters that control many aspects of algorithms' behavior. Some of these hyperparameters affect the time and memory cost of running the algorithm. The learning rate is perhaps the most important hyperparameter. If you have time to tune only one hyperparameter, tune the learning rate. When the learning rate is too large, gradient descent can inadvertently increase then decrease the training error. When the learning rate is too small, training is not only slower but also become permanently stuck with higher training error. Neural networks can sometimes perform well with only a small number of tuned parameters, but often it benefits significantly from tuning of 40 or more parameters. Unfortunately, hyperparameter optimization algorithms have their own hyperparameters, so which means that manual hyperparameters is time consuming and it takes a lot of resources also, and For neural networks, it's usually good to use automated hyperparameter tuning, where we have two common algorithms. First is grid search and second is random search. So for these algorithms, you need to give the range of the hyperparameters tuning. So maybe for learning rate, maybe from 0.01 to 0.001, or for the another parameter, maybe you can give range between 0 and 10. So grid search will select each one at one point and iteratively check the performance, and based on the performance it will return the best hyperparameter. But it is very, very expensive also if you have huge data set and complex model. But the result is that at the end of the day, you will benefit from, your model will benefit from these hyperparameters, and it will increase the performance metrics. So that's about hyperparameters. So let's talk about debugging strategies. This is very, very important, because when a machine learning system performs poorly, it is usually difficult to tell whether the poor performance is intrinsic to the algorithm itself or whether there is a bug in the implementation of the algorithm. Assume, for example, if we train a neural network on a new classification task and it achieved 5% test error, we have no straightforward way of knowing if this is expected behavior or suboptimal behavior. So usually it is difficult to debug, but there are two common ways for debugging. First way is that we need to design a very simple model, and in which model we can correctly predict the behavior which we expect. And by doing that, we can verify the correctness of implementation of the algorithm. Or we can design a test that exercises one part of the neural network implementation in isolation, by using some kind of unit test, maybe PyTest or unit test in provided language in isolation. So that's debugging strategies, and I prefer the second one mostly, because first one is not always easy to implement, but second one is checking in isolation, checking the shapes of the layers is good practice and easy to do. So, and in debugging strategies, so first thing is that we can visualize the model in action. If it is object detection, then we can check the rectangle of the prediction and see in action to understand how the model is working actually in practice. Second thing is that visualize the worst mistake. So when we test the model on the test set, and when we have these mistakes of the model, we can visualize these mistakes to understand where and how these mistakes are happening and how to overcome them. The third thing is that third strategy is reason about software using training and test error. So sometimes the software might have some kind of bugs, errors in implementation. So check the training error, check the test error, does it make sense or not? And the last debugging strategy is also good strategy, is that don't use a big dataset for training testing. Use small, tiny dataset. Check how model is performing on this small dataset, because you can verify many things in this tiny dataset quickly, because it doesn't need a lot of computation, a lot of resources, a lot of dataset. So you will understand the model behavior, most of the problems may occur. You can solve a lot of bugs by using the last one. So let's look to the example in multi-digit number recognition. So in the book, they provided the example where they have a project of street view transcription system, and there they are saying that they define the performance metric as first they select as a performance metric the accuracy of 98% and the coverage. They use the coverage and the coverage of maybe 95%. And then after selecting the performance metrics, yeah, I forgot about the goal. So their goal is to build the commercial application, which means they are not limited on not collecting the data, so that they can easily collect more data if they have a way. So after selecting these performance metrics and the goal, they build very simple baseline. As it is number recognition, they will deal with images. So they built very simple CNN model with ReLU activation function. And they give the output layer n different softmax units to predict a sequence of n characters. And after doing this very small model, they iteratively refine the baseline and test whether each change makes an improvement or not. So after doing this loop, they improve the model, and based on the paragraph on this section, they are saying that after doing this iteratives, then the network refused to classify an input x whenever the probability of the output sequence, probability of y given x, is less than this t for the sum threshold t. And the definition of probability of y and x is ad hoc. This motivated the development of the specialized output layer and cost functions that actually computed a principled log likelihood. So they build this threshold, and if the probability is less than this threshold, then there is no output, kind of. And by using this strategy, they also benefit, and they increase accuracy. And it said that they achieved the coverage of 90%, but they need 95 or 98. So what they did is that first they go and visualize the mistakes the model did. And when they checked the mistakes that model did, they understood that in some photos, the images, the numbers are recognized, some numbers are missed. For example, if we have 100, maybe like 2024, the model recognized only 024, not 2, not the first 2. So when they understood this kind of behavior, which they don't want the model do, they simply expand the width of the cropped region systematically, so that they achieved another 10%. They achieved another improvement, and then after doing that, they went and play around with hyperparameter tuning, and they achieved some kind of 1 or 2% of improvement. So this is example of how practical methodology in machine learning works. I hope this makes sense. That's it for today. If you have questions, ask in comments. So to conclude, that the practical methodologies in machine learning is not well constructed, not well defined, as in other computer science fields. But the point is that we should start from very, very small thing and iteratively improve it. And never jump to the complex one, because you may stuck in the complex one and waste a lot of time. Start iteratively from small iterations and achieve and improve the performance. That's it for today. So thank you very much. Have a good day. Bye bye.